Hey guys, Dr. J here, and in this video, we're going to start talking about magnetics and magnetic potentials. So just like gravity, magnetics also follows potential law. It's a potential field. And so there's going to be a lot of similarities between magnetics and gravity. There's also going to be some very important differences. They're not the same. And in particular, they're not the same because we're going to have to start thinking about electricity and charges and currents and things like that. But we'll get to that eventually here. And actually, we're going to start out by thinking about a couple of wires. So let's say we've got two loops of wire. Okay. And there's a current flowing through the wire. We'll call that current I. We'll call this loop B. And we'll call this current IA. So two wires, A and B. Loop B, loop A. They have a current flowing through them. And we can measure the kind of force component acting on a small element in this loop. So let's just say we have a little element, the LA, caused by an electric current coming through B, right, is given by the Lorentz force. So what do we have here? So this is going to be an incremental quantity. So we've got dFA. That's the force acting on this little part of the loop. We're going to have some constant, just like we had the gravity constant for gravity potential. We're going to have a constant for the magnetics. We're going to have our two currents. And those are equivalent to our two masses, right? We had the two masses of the two particles for the gravity law. Here we have our two currents. And then we have something a little bit different. So I'm going to have this quantity, and then I'm going to multiply it by dLA cross dLB, sorry, I'm running out of space, cross R divided by R squared. Oh, and let me just say, all right, here's dLB. Let me write this as a vector, dLA. So that's a vector, that's a vector. And then, what am I missing? The distance r. Let me not use r hat. R hat normally is a unit vector, so we'll just call it r is a vector. There we go. So now we have a vector r with a magnitude. The magnitude of that vector r is r with no line, and then it's in the direction r hat. So this is the basic equation. This is the magnetic force between these two little increments. And of course, we can think about, beginning to think about integrating around these loops, like we've already talked about. But I want to simplify this down a little bit because, as the book does, and write part of this in terms of something which looks more like what we talked about with the gravity field, right? So when we have the gravity field, let me just put that up over here for reference. We said gravity field or gravity force is equal to G mass 1, mass 2, divided by distance squared. And this is just the magnitude of the force, so we don't have that unit vector in there yet. I could throw the unit vector in there, r hat. Okay, that would be the equivalent. And then we said that was equal to something like mass 1 times g. Right, so this was our gravity field. That's a vector quantity. It's going to have a magnitude and a direction. So hopefully you can see here, this part here, we've got our two currents, we've got our two masses, we've got r squared, we've got r squared, we've got our constant. And then instead of, what do we have here? Instead of just r hat over r squared, we now have something which involves r hat over r squared, but it's more complicated than that. And it has to do with these little wire increments here. Okay, so what we'll do is we'll define something called capital B. And that'll also be a vector. And we're going to just pull some of these things out. Just like here, we had the gravity field. So this is going to be something like a magnetic field. And we'll have our current. And we'll have part of this component here, dLB cross R over R squared. Okay, now hopefully you can see this is what our our magnetic field is going to look like. If you remember here, our gravity field was capital G times mass 2 divided by r squared times r hat. So that should look very, very similar to what we have here, almost identical. Constant current divided by r squared, and then instead of just r hat, we have dlb cross r hat. So that's going to be our magnetic increment there. And of course, in order to go from that to actually B, we're just going to integrate dB around the loop of the current. So we'll do some kind of integral around the loop of the wire. And this is going to be called the Biot-Savart equation, or the Biot-Savart law. I can put this integral back in here, integrate this quantity here, and this would become B. Let me go ahead and do that. Okay, I'll put my integral in here, call this B. And again, this is a vector B. So this is equivalent to our gravity field, little g. Here we have capital B. This is for magnetics. This is our magnetic field, B. Or it's also called the magnetic induction, magnetic flux density, or simply the magnetic field. There are a couple different, there's going to end up being a couple different forms of the magnetic field, so we want to be careful about what we're talking about. But B, we can talk about the magnetic induction or the magnetic field, and that's a very valid way to call this. Now, if we do this, then we can also write our magnetic force in terms of B. What do we have left here if we pull this part out? We can simply write this dF term now. I'm going to rewrite that. Where am I going to rewrite it? I'll write it down here. dFA is going to equal, we got our current A, and then we need to have our dLA. And then that's going to be cross, you see that cross there, our dB terms. Did I get that right? Yes, dB. And of course, this is going to be dB of the B current loop. The increment in the magnetic force is going to be equal to the current times that little increment of, what do we call this, little wire increment, small element of the wire, cross the magnetic field coming from loop B. So loop B is inducing a field, which is interacting with loop A. That interaction is given by this cross product. We can also integrate that force. That's our basic definition. So B is going to be our magnetic field. Magnetic force is going to be how another charge particle or a wire is going to be interacting with that field. That's going to give us a magnetic force. So that's our basic magnetic force and magnetic field definition. All right, and this is reminding me to say, just like with gravity, you can have a gravity field without having any test mass or test particle. You can have a magnetic field without having any other current. The current in this loop of wire is going to generate a magnetic field, whether there's another wire to feel it or another charged particle to feel it or not. So now with gravity, what did we have? We had grad U is equal to G, right? We had the gradient of the potential is equal to the gravity field. And then we had del dot G is equal to 0 if we're outside sources. This is the same thing as del squared U is equal to 0. Laplace's equation, right? Laplace's equation if we're outside of all sources. And that turned into Poisson's equation if we were inside sources. For magnetic fields, we're going to have something slightly different. We will have del dot B is equal to 0. Magnetic induction has no divergence. So same thing as this, except this is going to hold even in the presence of sources, even in the presence of charges. So that means, by the way, that there can be no magnetic monopoles. Magnetic monopoles can't exist. So what we can do with this is we can use the divergence theorem to say something about how this works. So integral over a region, what's the divergence theorem say? Del dot B, right? That's the divergence, is equal to integral over a surface of B dot N. Make sure I get my vector notation there. Integrated over the surface. Divergence theorem, right? The integral over the surface of the normal component of that field is equal to the integral over the region of the divergence of that field. This is divergence theorem. So if this is equal to 0, well, this has got to be equal to 0. This whole thing is equal to 0. And so that means that the integral over the surface of B dot n equals 0. What does that mean? That means magnetic field lines that come into a region. Let's say we have some region. We have magnetic field lines coming in. Those same field lines have to go out. We can't have more field lines coming in or going out than the opposite. And again, this has to do with the fact that magnetic monopoles don't exist. Divergence theorem, based on this relationship, for all conditions, even with sources, says that you can't have magnetic monopoles. What this also means is that if you are able to measure the vertical component of the magnetic field over a large enough area, all the fields, all the ups and downs of the field should kind of eventually smooth out. You should get an average field of 0 if you're doing a magnetic survey. So this is actually very useful for geophysical surveys. Because of the fact that your ups and downs kind of need to cancel out, then you can actually survey a large enough area and you can measure the normal component, the component of the Earth's magnetic field coming out of its surface, and get an idea of what is happening to the magnetic sources that are inside. And again, they won't be magnetic monopoles, but what we'll see eventually is that they'll be dipoles. Okay, and that's what we're going to talk about. We'll kind of get to talking about that in the next video. We'll talk about dipole moments and vector and scalar potentials and things like that. So just setting up the some of the machinery here, magnetic forces and fields. Magnetic divergence of the magnetic field is always equal to 0, even in the presence of sources. That means you can't have magnetic monopoles. You don't have a region where you've got field lines pointing in towards a magnetic source, like you do with gravity. So gravity, the field lines point towards the masses. You don't have that with magnetics. You have field lines that are going around the dipoles. Okay, hopefully that makes sense. We'll talk more about this in the next video when we talk about vector and scalar potentials and dipoles.